Alright, we got a new microphone, so I hope the audio is better. Welcome to the second to last video of this series. We're going to be talking about friction today. I have a problem to do, and if time I'll have another one. So, let's do the first problem. There's a corner of the wall. Looks kind of like this. And there's a ball, a cylinder sitting there. And there is a wedge sitting there. The wedge is an angle of 30 degrees, and the cylinder has a radius of 0.5 feet. And we're going to call this interface C, this point B, and this point A. The cylinder weighs 8 pounds. And what else are we doing? Okay, the coefficients of static friction at A is equal to the coefficient of static friction at C, and is 0.5. Coefficient of static friction at B, 0.6. What is the maximum weight of the wedge? To remain in equilibrium. Well, I looked at this problem, and for a minute I was lost, and then I remembered the first step of any problem is free body diagrams. So, let's start with the cylinder. Draw this free body diagram. Actually, I'm going to do this on a new page. We have a normal force here and a friction force here. Which way is it going? I don't know yet. Come on. And normal force for the ball here. Let's do the. I don't know which way to look. So let's do the wedge real quick. This is 30 degrees. The weight. There's a friction force in the wall. Normal force at the wall. Normal force at the ball. There is a cylinder. And friction force at the cylinder at point B. Because of gravity, which is always accelerates things towards the Earth, we know that the cylinders try to move down. So the friction forces are going to be opposite that movement and are going to be pointing upwards along the surface. So notice this is straight up. This is along the surface, perpendicular to this normal force. And then if you would like to do some geometry, we know that this is 60 degrees and this is 30 degrees. So if we go back to our cylinder for a second, we found that friction force at FB was pointing up for the wedge, which means it's going to be the opposite effect at the opposite point, just like the normal force. So we're going to draw it like this. And we also know this is 30 degrees and this is 60 degrees. So that's nice. We know the weight. And then we think about how this would move. Well, I'm not really sure how it would move. It's rather confusing. So I'm just going to point it to the right so that we have a positive friction force here. And we'll find out that that works fairly well All right, so if we list our unknowns, we have quite a few. We have the normal force at A, the friction force at A, the normal force at B, the friction force at B, the normal force at C, and the friction force at C, and the weight of the cylinder. This is 7 unknowns. And how many equations do we have? Well, we have 2 for the wedge and 3 for the cylinder. We have the Newtonian forces, and the cylinder is also going to have some of the moments. Well, those aren't enough equations. So at some point, we will have to assume they're slipping somewhere. But we'll figure out where as we go along. All right, start with the cylinder. We are going to start with, we're just going to list out these equations. So sum of the forces in the x is 0. What is it I'm going to put over here? Oh dear. Oh yeah, coordinates this one. This will give us minus the normal force at B times cosine of 30 plus friction force at B times cosine of 60 plus the friction force at A equals 0. Sum of the forces in Y is 0. That will give us the normal force at A minus the weight minus the normal force at B times sine of 30 degrees minus the friction force at B times the sine of 60 degrees is 0. And finally we get a moment. I only get 1 moment per free body, from 1 moment equation per free body diagram. So we have to choose this point carefully. So what this comes down to is the distances. If you pick point A or point B, at some point you're going to have to calculate that distance, this distance, or this distance, which is no fun. I personally do not like calculating lines through circles. But if we pick the point to be the center, we know these perpendicular distances. It's the radius, which is half foot. So, during consideration, we are going to use the center. Oh, wait, we already have C. We'll call this point O. And so we use forces and perpendicular distances. NA does not have a perpendicular distance. It's pointing along the line. So that's nothing. FA, perpendicular distance is 0.5, and it's pulling it counterclockwise, so it's friction force at A times 0.5 feet. And then NB is pointing along that line because it's perpendicular to the tangent line. FB is 0.5 feet and it's pulling it clockwise, so it's minus friction force at B times 0.5 feet equals 0. That tells us that friction force at A is equal to the friction force at B. And at this point, we don't have enough equations. We could go to the wedge, but I'll tell you right now, it's not going to give us anything. But we know that that point B is the common point between the cylinder and the wedge. So we want something that takes everything that's in terms of A from the cylinder and puts it in terms of B. Because the wedge doesn't know that point A exists. I'm going to write this down. The wedge does not know point A exists. So therefore you want to put all wedge equations in terms of point B. And to do this, we are going to assume that it slips at A, which means that the friction force at A is equal to the static coefficient for A times the normal force at A, or 0.5 A. Now we can put that into some equations. This will give us that the normal force at A equals 2 FB if we put it into here. If we put it into here, we get 2 FB minus 8 minus NB sine 30 minus FB sine 60 is equal to 0. And that will come out to be, that will simplify to FB equals 0.441 NB plus 7.08. We put that up here, we get minus NB cosine 30 degrees plus FB cosine 60 degrees plus FB equals 0, and we will get FB equals 0.577 NB. We take these two equations and we plug them and we compare them. So we say that 0.577 NB equals 0.441 NB plus 7.08, and we get NB equals 52.1. That means that friction at B equals, hold on, I didn't do this beforehand. Is 30.1 pounds. And if we wanted to, we could then use those to find NA and FA, but we don't need those. So we're just going to take these and take them to the wedge. So that was correctly? Yes, I did. Okay. All right, let's do our Newton here. All right. This will be sum of the forces in the x equals 0. The normal force at point B times cosine of 30 degrees minus the friction force at point B times cosine of 60 degrees minus the normal force at C equals 0. This will give us the normal force at C is 52.1 times cosine of 30 minus 30.1 times cosine of 60 is 30.1. and pounds. And the sum of the forces in the y equals 0. And that B and B sine 30, sine 30 degrees plus F B sine 60 degrees plus the friction force at C. Let's do this one. NC equals, minus the weight equals 0. And so plugging some numbers. Sine 30 plus 30.1 sine 60. 52.1 plus FC equals weight. So we have 2 equations and 3 unknowns. We need 1 more equation. And we notice that there's FC here and NC here, so we want an equation that does that. So again, we assume slipping at C. So FC equals mu static at C and at C, which is 0.5 times 30.1, which is 15.05, which means the weight is pounds, 67.15 pounds. And the answer at the back of my books is 66 pounds, which is within error, I believe. 67.15 minus 66 out of 66 is 1.7%. So it's good. That's an engineering okay. If it's within 5%, it's an engineering okay. That's the benefit of engineers. We don't have to be perfect. We just have to be close to perfect. Like me, I'm pretty close to perfect. So, and then the internet said that if we go back and we have, if we multiply 52.1 times, I'm going to use blue for this actually, 52.1 times 0.6, which is the coefficient of static friction of B, we get 31.56, which is greater than 30.1. So, assuming slipping at friction of B would not have been good. So, looks like we got the right answer there. See if we have time to go over that other problem. I thought it was a tricky one, and it's an example in an old textbook I found. So we have this. There's a pin here, just attached to a beam. The beam is supported at this end by a pin. And this point C, this point B, this point A, and there's a distributed load up here. 200 newtons per meter, and this is 4 meters. This is 1 meter, and we apply a force P here that is 0.25 meters from the bottom. Coefficient of static friction at B is 0.2, and the coefficient of static friction at C is 0.5. And we want P minimum to remove that beam from underneath this beam. The post, they call it post BC. And so the question is, which is going to flip first, C or B? Well, really the only way to do that is to solve for both. First, free body diagrams. So, this being we have 200 newtons per meter, normal force at B, friction force at B, and Y, and the X. Oh, and the X going the other way. So, some of the forces, oh, right, and in the post, we have P and C, and B, B. Some of the forces at X equals 0. Always define your coordinates. P minus FB minus FC equals 0. Some of the forces, Y equals 0. Oh, right, they want some of the moments about A equals 0. FB isn't going to require a moment because it's along the axis. We get 4 times NB plus 2 times 200 times 4. This is 4 over 2. This is how we have 2. 0. This should be minus. And we get NB equals 400 newtons. Over here, we get NB equals NC. NC equals 400 newtons. So now we have some equations. Oh, and some of the moments about C, we get 0.25 P equals FB. This is 0.25, this is what, this axis on the axis. So we have these equations. We have FB equals 0.25. We have NB equals 400 newtons. We have MC equals 400 newtons. We have, what else? P equals FB plus FC. And the coefficients of static table show you 2 mu C equals 5. All right, so case 1. C, B only slopes. We're going to start with B. And we're going to get, so that means that F B equals mu B NB equals 0.2 times 400, which is 80 newtons. We put that into the moment equation. We get P equals 4 times 80 newtons. P equals 320 newtons. This would give us that the friction force at C is 240 newtons. But if we assume no slipping, this is greater than mu C NC, which is equal to 0.5 times 100, which is 200 newtons. This would mean that if it slipped only at B, FC would already have slipped, which doesn't make any sense considering our first assumption. Therefore, this assumption is wrong. So we write another assumption. 2 slips only at C. For FC equals mu C NC, which is equal to 200 newtons. What's else? P equals 4P times 0.25, 0.75 P equals FC. P equals 267 newtons. FB equals 66.7 newtons. This is lower than this. This is lower than this. Therefore, P min is 267 newtons. So, that's your answer. All right. That's friction for you. I think we're all done here. See you next time.